The introduction. So the title of the thesis is, I have to read it, Strategies for Molecular Engineering of Macroscopic Adhesion and Integrity, focusing on cellulose-based materials. I thought I would start with some acknowledgement. I'd like to thank the Swedish Research Council for their funding of this work. And of course, I'd like to thank my main supervisor, Lars Wågberg, for his support and guidance. And also my co-supervisors, Eva Malmström and Anna Carlmark. And also Torbjörn Pettersson and Samuel Pendergraph has been very valuable in this work. And of course, I'd like to thank all my co-supervisors or co-authors who have helped in all the studies in the thesis. And my colleagues, of course, at FPD, especially within the coating and fiber technology groups. I thought I'd start with this pretty picture of plastic debris on a beach. I'm sure you've seen pictures like this in the newspapers many times. Marine litter is one of many struggles we have today in regard to the environment. It poses a problem both to fauna with ingestion and entanglement, and also directly to humans, both in regard to consuming animals, which have in turn ingested plastic materials, and also it poses an economical challenge when beaches look like this. It's not as many tourists around, of course. So that's one of the struggles we have with the plastic materials of today. Their persistence in nature, which, if they're not handled correctly, can lead to this because due to their non-biodegradability. And then they're also based usually on petroleum, which is a non-renewable resource, which from a sustainability perspective, of course, isn't ideal. But there are, of course, also reasons that we are using the plastic materials. For one, they can protect the quality of transported goods. They also help in reducing food waste, which is another main environmental concern we have. For instance, a cucumber packed in plastic will last for a much longer time than if you leave it unprotected. And plastic is also used in milk and juice packages as a barrier. This barrier properties usually isn't incorporated in the cardboard that makes up the bulk of the package material. And not to mention the convenience of the plastic materials. But it would, of course, be nice to, when we can, exchange the currently used materials for biodegradable and renewable alternatives. Cellulose, as the most abundant biopolymer we have on the Earth, is of course a very interesting and nice option. It is biodegradable and renewable. It is a stiff and strong material, and therefore it is already used in both paper and cardboard in a broad range of applications. The ductility and formability of cellulose is, however, not very high, which makes it difficult to directly replace many of the plastic materials with cellulose. So to further widen the utility of cellulose, there are several strategies investigated, but one would be to modify the cellulose structure to increase the ductility, or to modify the cellulose joints, or to use the stiffness and strength it has intrinsically and use it as a reinforcer in a composite material. In both these types of applications, it's important to know about the interactions across interfaces within the material. So this brings us to the objective of this study, which was to look at strategies to control the adhesion or interaction across an interface, and also to tune the interaction across an interface. We looked at 3 different tracks. In one of those, we studied the layer-by-layer modification of surfaces and how this could be used to alter the adhesion between those layer-by-layer modified surfaces. We also utilized very smooth cellulose probes and evaluated how we could use those to study chemically modified cellulose surfaces and their adhesion. And then we made 2 composite materials using cellulose as a reinforcing component, using 2 different strategies to ensure that we had the distribution we wanted of the composite components and the interaction we needed between the components. Before going into more detail about those, I thought I'd say a few words about adhesion. So in essence, adhesion is the phenomenon where surfaces coming to and stay in contact. From a thermodynamic point of view, adhesion can be described as the work needed to separate an interface, 1, 2 here, into 2 new surfaces, 1 and 2, with surface-free energies 1 and 2. This is provided that this process of forming the interface and then separating it again, forming the two free surfaces, is fully reversible. Usually, or very often at least when you measure adhesion, you will encounter values which is higher than the thermodynamic work of adhesion. For polymeric interfaces, two common reasons is either, or a combination maybe, of interpenetration of the polymer chains, and dissipation due to viscoelasticity, energy dissipation due to viscoelasticity. One way of evaluating adhesion is to look at the contact mechanics, which is to evaluate how the surfaces deform when they come into contact. A very early model to look at this was developed by Hertz in the late 1800s. In this model, however, the surfaces just deform due to the pressure they exert on each other. There is no adhesion incorporated in this model. Roughly 100 years later, the Johnson-Kendall-Roberts theory was presented, which is a model which describes the adhesion or the deformation due to adhesion between elastic surfaces. Here you see their equation. It relates the contact radius of this interface to the JKR work of adhesion. And I will get into a little more detail about all the components of the equation later, when it becomes relevant to the data evaluation. So then, on to the first track with a layer-by-layer assembly to modify adhesion. So here we synthesize tri-block of polymers with long hydrophobic mid-block, which dissipated energy, and short anchoring outer blocks of either cationic or anionic nature. These tri-block of polymers formed micelles in water dispersion with a hydrophobic core and a charged corona. And then we use those charged micelles to build up this layer-by-layer structure, alternately absorbing the cationic and then the anionic samples. And then we looked at the adhesion of those layer-by-layer modified surfaces. We chose to make tri-block of polymers with two different middle-block polymers. This was either butyl methacrylate or polybutyl methacrylate with a TG around room temperature, or polyethyl hexyl methacrylate with a TG around -10. We chose them because we wanted to study what effect the difference in TG had on the resulting LBL structures. We also made a longer version of the PEHMA containing micelles to study what effect this difference in molecular weight would have on the adhesion. All polymers were synthesized through atom transfer radical polymerization, a controlled radical polymerization technique. And the naming you see here is used throughout the presentation, where S stands for the shorter version of the polymer, L for the longer version. Then we have the middle block, and the plus or minus sign shows the charge of the outer block. As you can see from the dP values, we had a substantially longer middle block than outer block on the polymers. So after making the tri-block of polymers, we created the micelles by first dissolving the polymer in a co-solvent that dissolved both blocks, and then dropwise adding this polymer solution to water under agitation, and lastly dialysis to remove the co-solvent to have a pure water-based micelle dispersion. Here you see some values result from dynamic light scattering. As you can see, the hydrodynamic diameter of the micelles with the longer and shorter PHMA containing polymers had a very similar size, despite the difference in molecular weight of the polymer. We used quartz crystal microbalance to evaluate the absorption or LBL buildup of those micelles, and it showed that all micelle systems adsorbed in multi-layers. This graph is of the longer PHMA containing tri-block of polymers, but the behavior was very similar for all systems. The absorption was higher when we had salt present than if we had used pure molecule water. This is common for charged polymers due to the ions in solution screening the charges on the polymer, and then they can pack closer together on the surface. So then I will mention a little bit about the results from the adhesion measurements on the LBL treated surfaces. We used atomic force microscopy to evaluate the adhesion. This technique can also be used for topographical imaging with nanoscale resolution of a surface. Typically then you use a piezoelectric cantilever with a sharp tip. This tip is usually in the nanometer range. And when you scan the surface using this cantilever, it will bend as the tip encounters a topographical tip or valley. And using this laser that is reflected off the back of the cantilever and the place in which it reaches the detector, we can then use this data to get information about the topography of the surface. But we can also use the EFM technique to look at forces between surfaces. Commonly then, we instead of the sharp tip use a spherical probe that we glue onto a tipless cantilever, simply because the spherical geometry is well defined and it makes the data evaluation more feasible. This is an image to give an example of how it looks, one of those cantilevers with a probe glued to it. The radius of the probes we used were around 4 micrometers, but every single probe used was measured individually, but to give you a feel of the size. And then, as mentioned, we looked at the adhesion between LBL-treated surfaces, but the technique could, of course, be used to study the interaction between other types of surfaces as well. This is a short animation illustrating how a measurement is performed. The two surfaces are brought into contact, and then they are pulled apart. And as you can see, the cantilever bends as a result of this interaction. This is the same measurement again, but now also showing how the laser is reflected off the back of the cantilever and reached the detector. So this data, together with the stiffness of the cantilever, the spring constant of the cantilever, and the deflection sensitivity, can then be used to calculate the force between the surfaces. This is a graph showing the normalized force versus separation for the shorter, softer system. As you can see, we have an increase in pull-off force as we increase the number of bilayers added. This is a comparison with the stiffer polymer system. And here we have the opposite trend, where we decrease the pull-off force as we increase the number of bilayers added, which we believe is a result of the stiffer nature of those micelles. They were likely not able to conform to the underlying substrate or underlying layer as well as the softer one, and therefore we probably have less fundamental interactions and electrostatic interactions between the layer as we build them up, which result then in less adhesion between the surfaces. When we looked at the longer PHMA-containing micelles, and we studied them with no dwell time, i.e. we just brought the surfaces together and then pulled them apart immediately, we had a stronger adhesion between in the shorter system than in the longer system. But when we looked at the same systems with 30 seconds dwell time, so we brought them into contact and let them rest for 30 seconds before pulling them apart, there was a different behavior of the micelles. We believe that this is due to probably the lower chain mobility of the longer micelles, so they may need more time in contact to be able to form interactions between the two surfaces. Here are graphs shown from measurements with 30 seconds dwell time, and we also had 5 millimolar salt present during the adsorption steps to build up the LBL structure. Please note the difference in scale on the two systems when you compare them. To give some sort of context to these results, I wanted to mention a study where they evaluated a system containing muscle foot protein with colloidal probe EFM. This muscle foot protein is widely regarded as a strong underwater adhesive, allowing muscles to attach to rocks, also in high current underwater. In this study, they obtained a pull-off force around 130 millinewton per meter. And as you can see from those graphs, we are in the same range, or maybe slightly above. So we have a system that is rivaling the wet adhesion of muscle foot protein. The pull-off force is fairly similar between the shorter and longer LBL system. But we have one marked difference, and that is the separation at zero force, which is what is highlighted by the arrows in the graph here. As you can see, for the longer system, we reach values about 1 micrometer, whereas it's fairly consistent around 250 micrometers, or nanometers, sorry, for the short system. We believe that this could be due to a transition from below to above the entanglement molecular weight, or PHMA, which then allows the longer system to entangle and then retain or keep interaction between the surfaces over a further separation. Here is a theoretical estimate of the length of a fully extended chain of the shorter and the longer micelles, or the tri-block polymers. This is calculated by using the theoretical length of a carbon-carbon bond and the angle between the bonds. And as you can see, even for the shorter system, we have interaction over a longer separation than the length of one polymer chain. So there must be several interacting polymer chain to bridge the gap between the surfaces, even for the shorter system. A short summary of this track before moving on to the next. So we made those tri-block polymers with long hydrophobic energy dissipating middle blocks and short charged outer blocks. They formed micelles in water dispersion, which were used to build up those LBL structures on surfaces. And the adhesion between those LBL surfaces was in the range of that of muscle-filled protein. So then I will move on to the second track, where we study the adhesion of chemically modified cellulose surfaces. So when you study adhesion, you usually at least want very smooth surfaces, because most adhesion forces are very short-ranged. So if you have surface roughness or contaminants or something on the surface, you may obscure the adhesion forces. If you want to study cellulose, one method to obtain very smooth surfaces is to spin coat a thin cellulose film from a cellulose solution onto a support. This is, of course, it is a very usable method, but it does produce a very thin cellulose film on a rigid support, so it will produce a cellulose material that is confined. And it is known that generally it's not only the most superficial layer that is important for the adhesive response of the material, also the bulk material is important. So it would be desirable to also be able to look at cellulose that is smooth, but also possess a bulk material response. For this purpose, and other purposes as well, we have previously in the group developed a way to create nanometer smooth cellulose spheres. The spheres used here had a roughness between 3 and 9 nanometers measured through AFM, and a diameter between 0.6 and 1 millimeter. So what we did here was to chemically modify them by grafting PDMS, or polydimethylsiloxane, from the surface using ring opening polymerization. We grafted 3 different lengths of PDMS. We named them short, medium, and long, referring to the relative length. And then we used them in contact adhesion testing measurements, which I will describe a little more. So this is a schematic illustration of this contact adhesion testing setup we used for the adhesion measurement, where we mounted the cellulose bead on a scale or an analytical balance, and then we tested this against a PDMS elastomer, which was mounted on a sample holder, which in turn was attached to a motor to be able to finally control the distance between the samples. And when they are in contact, we can look at the contact area between the two surfaces using an optical microscope. This is a short animation, again illustrating how the measurement is performed, bringing the surfaces into contact until we reach a certain threshold value on the scale, and then we pull the surfaces apart again. And here is a sped up version of the progression of the contact area viewed through the optical microscope during the measurement, together with the other data we record simultaneously, which is the motor precision, which then reflects the distance between the surfaces, and the load measured on the balance. Right, soon finished. I'll let it finish. And then we use the JKR equation to evaluate this data we have obtained from the measurements. R in this equation relates to the radius of the probe. At least in the setup we use, when we have one flat surface and one spherical probe, it will relate to it will be the radius of the cellulose bead. Then we have an elastic constant in the equation, and when we have the setup we have with a relatively stiff cellulose bead against a much more ductile PDMS surface, this elastic constant will be dominated by the elastic response of the PDMS elastomer. A is the contact radius between the surfaces, and F is the load measured by the balance. And by fitting the JKR equation to this plot, we can obtain the JKR work of adhesion from the data. Another parameter we can look at is the critical energy release rate. We then take the force at the position or the point where the two surfaces critically separate, again inserting the radius of the probe, and then we can calculate the critical energy release rate as well. In this graph you see those parameters. We have work of adhesion for the loading or the approach part, and also for the unloading or retraction part of the curve, together with GC. As you can see, there is a substantial difference or increase in adhesion for the longest grafting length compared to the shorter ones. A previous study has found that the entanglement molecular weight of PDMS, the polymer we have grafted, lies between the length we have on our medium and long grafts. So we believe that this transition or this marked difference in adhesion is due to us being above the entanglement molecular weight of the polymer for the longest grafting length and below for the lower grafting lengths. So a short recap of this part of or this track before moving on to the third one. We used those nanometer smooth cellulose spheres and chemically modified them by grafting PDMS from the surface using ring opening polymerization. We then used those spheres for adhesion measurements in the contact adhesion testing setup, and found that when we were above the critical entanglement length of the polymer for the grafts, we had a substantial increase in adhesion. So then I would move on to the last track, where we made composite materials using cellulose as reinforcer. So when you want to make a composite materials, in most cases at least, it's not sufficient to just mix them and hope that you get a nice material. You usually have to employ some strategy to ensure that you have favorable interactions between the materials in your composite, and that you have a good distribution of the components among each other. So I will present two composite materials, one where a compatibilizer was used to enhance the interaction between polycaprolactone and cellulose nanofibrils. And in the other one, instead an interpenetrated network was created of polyacrylamide and CNF. So first a few words then about this PCl CNF composite. A compatibilizer polymer was designed and synthesized. It's named MX. It contained a coordinized amine in one of the side chains for the cationic charge, which then allowed it, and then also another monomer, polyhydroxyethyl methacrylate. Due to the cationic charge, it could be absorbed onto the anionic surface of those cellulose nanofibrils. In addition to the cationic charge, also those other monomer groups were modified to allow a covalent bond to PCl upon addition of a radical initiator to the mixture. So then by first adsorbing this MX polymer to CNF, and then mixing those MX-treated CNF with PCl in the presence of a radical initiator, this interface could be formed where the MX polymer is both electrostatically adsorbed to the CNF and also covalently linked to the PCl matrix. Here are topographical AFM images showing the untreated CNF fibrils and then the CNF fibrils treated with MX. And as you can see, we have a morphological difference between the two. We also mapped these surfaces looking at the relative modulus over the surface in the AFM, and found that the modulus over the neat CNF was between 10 and 40 gigapascals. And for the MX-treated fibrils, we had a homogeneously lower modulus over the surface between 1 and 4 gigapascals, which then indicates that we have a homogeneous coating of the fibrils with CNF, since we don't see any spikes of higher modulus. Here are SEM and AFM images of a composite in the bottom row, So then we have MX-treated CNF fibrils added to the PCL, and in the top row we have a reference with untreated CNF fibrils added to the PCL. And as you can quite clearly see in the SEM images, the morphology is quite different, with what appears to be large CNF aggregates in the reference sample and a more homogeneous surface in the composite material. In the AFM images, the overlay or the color reflects the modulus over the surface again. And again, we have a much more homogeneous modulus in the composite material, whereas we see spikes of a much higher modulus in the reference sample, which we believe then to reflect places where we have CNF aggregates. And just to give you a short feel for the mechanical properties of the composite material, I wanted to show you a few graphs from mechanical evaluation. The samples highlighted by the box are the composite samples. The difference between the two composites is just that we had more radical initiator in one of them, so likely a higher than number of covalent bonds between MX and PCL in this composite. But as you can see, both the Young's modulus, the ultimate strength, and the storage modulus was increased for the composite samples compared to the reference samples. With that, I'll move on to the other composite material, consisting of an interpenetrating network of polyacrylamide and CNF. We have previously in our group developed a method to create very porous CNF aerogels, which are also wet stable by cross-linking the CNF. Here you can see an SEM image of the internal structure of one of those aerogels, showing the porous and relatively open structure. To create this composite material, we polymerized polyacrylamide within the pores of the CNF aerogel by first soaking the preformed aerogel in the monomer solution, also containing a cross-linking monomer, and then transferring the soaked aerogel to another solution containing the initiator, and then initiating free radical polymerization of the polyacrylamide. Here you see SEM images taken at cryogenic temperatures of the composite, showing the polyacrylamide within the pores of the CNF aerogel. If we look at the compressive test of a neat CNF aerogel that is soaked in water, we see that it releases its water under compressive load, but then it will reabsorb the water and regain its shape when you release the load again. The water in those images has been dyed with a food colorant to increase the contrast in the images. If we look at the neat polyacrylamide hydrogel, it will not release the water when it's compressed, but it breaks relatively easily. The composite sample, on the other hand, was able to retain the water under compressive load to a higher degree, or until a higher stress was reached, without releasing the water it had absorbed. This behavior can also be seen in this compressive stress versus strain graph, with the green curves showing the composite. And as you can see, it has a more than double stress at break compared to the polyacrylamide hydrogel. This graph also shows you the difference between never dried and reswollen samples, with the dashed line showing the samples that had been dried and reswollen. And for the composite, we had a very little difference between the two, whereas for the polyacrylamide hydrogel, the stress at break and strain at break is half, basically, when we have dried and reswollen samples. As you can see in those images that are taken during and after drying of the samples, we have visible cracks in the hydrogel, whereas the composite material is able to retain its shape to a higher degree during the drying process. So, very short summary of the composite materials. We utilize the compatible isopolymer to enhance the interaction and distribution of CNF in a PCL matrix to create a PCL CNF composite. We also created an interpenetrated network of CNF and polyacrylamide, with polyacrylamide present throughout the pores of the CNF aerogel. And we found that the composites had a much higher stress at break than the neat polyacrylamide hydrogels. This almost wraps up the presentation. I will just shortly summarize and conclude the whole project. So the overall aim was to elucidate strategies to measure, to tune, and to control the interaction across an interface. We looked at tri-block polymers, which self-assembled in water into micelles with hydrophobic core and charged corona. We then used those micelles to build up LBL structures on surfaces to be able to modify the adhesion of the surface. And we found that we had wet adhesion rivaling that of muscle foot protein between our LBL treated surfaces, and that we could tune the adhesive properties of the surface by adjusting the number of bilayers we added, and also the middle block chemistry, and adjusting the molecular weight of the polymer added. And then we demonstrated that we could use chemically modified and very smooth cellulose surfaces for adhesion measurements, and found a dramatic increase in adhesion when the grafts were above the entanglement molecular weight of the polymer. And lastly, we created 2 composite materials using cellulose as a reinforcing component, using 2 different strategies to ensure a good distribution of the composite components and interaction between them. In one, we had a compatible isopolymer between PCl and CNF, and in the second, an interpenetrated network of polyacrylamide and CNF. So with that, I'd just like to thank you for your attention.
Thank you very much, Andrea. Now I would like to invite the faculty opponent, Professor Master Träger.
Sit down.
Yeah, if you want to, either sit down or stand up, as you wish. Maybe I take these flowers so that you can be seen by the audience.
Thanks for a very interesting array of results. Is it okay like this, or?
Should we use a mic?